probably come to the conclusion that the CRC hardware implementation is actually better because it sort of gives a good middle ground between contradictory demands of area and power. This is so far that we did for ASIC ARM setup.
And so can you just intuitively tell me why CRC actually is better in hardware for power, much better in hardware than in software?
Yeah, because the CRC operation is totally division, XORing, bit shifting operation.
It's a lot of calculation area.
It's a lot of calculation. So anything, usually it's intuitive that whatever is a lot of all these kinds of calculations is better done in hardware because it's less power compared to software.
It has to run at the peak bit rate, whereas many of the state machines don't run at the peak bit rate.
Yeah, the frequency required for its operation in software is like gets really high, especially when it has to be done continuously for like a large packet size. Then once the frequency shoots up, the power demand.
So you should point out that the 11 megabit case is where you have go back to. So explain what it means to be at 11 megabit here.
11 megabit means I'm actually doing all the bit operations at 11 megahertz for the hardware system. But for software, it's not 11 megahertz. It can be very high, as much as maybe 70-80 megahertz also, because that's when I am counting the number of instructions, counting the number of cycles, then multiplying it by the number of times clock cycles the module has to execute, and that gives me a very high frequency for software, so the power was really high.
Power actually, is it only the frequency, or I thought if you take a CMOS thing, the number of switching is matters. For example, a CMOS, dynamic CMOS is only from 1 to 0 transition, power is distributed.
It says that all this is done for the ASIC and the Xilinx one, because that's where the CMOS transistor comes in. For the software, I have done the calculation, so there I have included only the frequency of operation required for power. This is an approximation, but still I think it's a...
I think it's a lot of work to count the number of transitions from 0 to 1.
Yeah, that's...
pseudo-random bit like that.
But that is happening in the tool. I mean, they have some approximations for that. But Mike Bushnell had a couple of PhD students who are working on how to improve that by reducing number of transitions. It's called glitch removal type of thing. But that goes deeper. This is at a system level. That's more at the chip design.
So power consumption is just taken from the tool, from numbers.
Yeah, that's whatever cadence.
Yeah, so Xilinx and ASIC targeted for the synthesis libraries and give it. But the problem is usually making the code work for the synthesis library because, like I said, all the abstract things have to be converted into clearly explained. Okay, we did the ASIC system. The same exercise that I did for an ASIC ARM system, I did for an FPGA system. And there are some figures here which might be a little surprising because even though the FPGA is supposed to be power optimized, since the ARM processor is so power conservative, actually the all FPGA system gives a high power consumption as compared to an all software system here. So in between there are two other combinations, not all software, sorry, the CRC then hardware. The other two combinations are a little higher than the CRC hardware, but again here this system configuration seems to give the best power dissipation. We still have to look for the area before we decide that even for an FPGA ARM system that this should be the probable implementation. That exercise was performed for 128 bytes and for 502 bytes. And obviously when you look at the power, you probably want to conclude that the CRC hardware system is best. What you have to keep in mind is even you cannot just dismiss off the FPGA just like that simply because even though the power dissipation might be high, finally when you're actually developing your design, the FPGA is probably what you will end up using to test it. And the ASIC, since it's the very last stage of the design, it won't come into your power calculations before that. And this is what the system costs show. So when I have a system configuration which is moving slow, migrating slowly from all FPGA to only one module, which is a CRC in the FPGA, this is how the system costs appear. So the area change is not very much because most of the area change there is more the CRC module which occupies most of the logic gates in the design. Because the state machines are pretty much optimized to occupy the area on the chip, the tool automatically optimizes them. So the area really for the entire design matters more on the packet creation and the CRC modules. And obviously the all hardware gives, all FPGA one gives the highest power and more area. So probably you can come to the conclusion that the CRC hardware implementation is better even for an FPGA ARM system.
How does that power number there, when you have the CRC in the FPGA, how does that compare with the all software power number?
The all software one, with the power number. It does, but see then the thing is, if I'm comparing the ARM core with the FPGA, that's not a very fair thing. If I had an ARM core on the FPGA itself, then probably I could implement it there and compare the power.
I think she's asking it from an extrinsic point of view. Should I use FPGA or should I use an ARM chip which is optimized? So what are the two numbers?
So if you put the CRC into software as well, what's the next point?
If I put the CRC into software as well, the power is pretty low actually.
You have the result from the
Can you look it up on the previous chart? Or like
No, I
no, further back.
No, this one is the FPGA one where I don't have the all software configuration at all here.
No, go back to your all software.
But when you had the ASIC, you had all software configuration. Right? So, what was the equivalent power level there in milliwatts per?
The power is
12 milliwatts. So
12.
go to the slide again.
That was 11 megabits per second, right?
yeah, and you are looking at this one?
So this is 1 megabit.
1 megabit. Oh, this plot that I've done is for 1 megabit actually. Oh, you can look at that one also for 1 megabit. This is ASIC 1 megabit, yeah.
So 1 megabit, it's about 3 milliwatts.
3. I think the FPGA in terms of power is like nothing below in the two starts below 25 milliwatts. There is an offset. I did not take the incremental power into consideration.
Okay, so you just adopt the DC power essentially.
It does have.
Factored into it, because when you look at this curve, you would ask the question, why would anyone ever build anything in an FPGA,
yeah.
right? Because it wouldn't make any sense.
They have a lot of money and their management is requiring that you do.
I mean, if you can build a solution in a processor that's lower power than the FPGA, it doesn't make any sense. Right?
Yeah, I remember the incremental fact that I was probably supposed to have looked at, but when I decided to plot, I took the absolute figures into mind. So what happens is basically any code that I simulate in Xilinx and input into X power, for Spartan 2E, the design starts with a basic offset of like say 25 milliwatts. So when you compare that to the ARM, probably you should take that off and then compare the incremental power. Okay, oh, sorry. So the FPGA system costs were the graphs that I was discussing. And if you look at these for 128 byte and 502 byte packets at 1 Mbps, you get to the conclusion probably that even here, considering both system power and area descriptions, the CRC hardware implementation appears to be a good compromise in terms of your system parameters such as your packet size, the data rate, and the cost of development. And this is not to write off FPGAs at all, but rather to say that they are much more, they have the reconfigurability advantage. So probably the design development will use an FPGA and ARM in the initial phase and end up with an ASIC and ARM implementation as a final result.
That's for testing the intermediate design, right? Before I actually build it on everything.
Yeah, you would test it.
Most of the telecom companies do release products with FPGAs. That's kind of a culture. Most Lucent and this kind of companies routinely the first generation of product has FPGA and they lose money on those and they're more power hungry. But that's, it's a culture of putting out the product.
You win the socket that way from the customer, and then you come in with a cost reduced. Well, once they're completely wrapped into your solution, they can't do it any other way. Then you can bring in that.
It cuts maybe 6 months of development time, but it's arguable that you could always go directly to ASIC as well.
The event execution is FPGA ASIC, which is better.
It's not an apples to oranges, it's not really a direct comparison. It's mostly about cutting development.
those decisions are made most taken by the developers. Probably the decision comes from finance.
So I think with these results they're meant to do some benchmarking of what different modules you can take out from software or hardware and try to see the balance. So in the Muse project, our objective was to build a low power 802.11 device, and this shows you that you can get down to orders of 10 milliwatt, 20 milliwatt type of power level, and at the bit rate 1 megabit, which is sufficient for many sensor applications, looks okay. And then further tuning of whether to go all software or not. So the all software solution is always a bit worse than software plus a little bit of ASIC. So that seems to be the. It's interesting. The same conclusion was reported in '95 by an MIT group for ATM SAR, where it turns out that if you use the ARM, optimize ARM with the CRC, that's probably the best you can do to optimize the ATM SAR. So it's a very different statement in SAR.
Yeah, so since I've shown the results that I plotted for both the different targeted platforms, let me come to the conclusion. So the aim was to propose a methodology with which we could partition the system effectively. By partitioning, I meant 5 different system configurations were considered. Obviously, many more can be studied. A more fully developed Mac could also be studied where the RTS has also been implemented. But so far, with what I have implemented, I targeted those on 2 different platforms, which were the ASIC and the ARM and FPGA ARM. So the aim was to find a good middle ground, a compromise between area and power requirements, because with ASICs the power is really low but the area is very high. The reverse is true for a software implementation, but somewhere in between you find a good partition which satisfies your system needs. And all these system values have been calculated for the typical 802.11 channel rates, which were 1, 11, 5.5 and 11 Mbps, and 2 different packet sizes of 128 bytes and 502 bytes. So, and finally, from both these system implementations, the CRC hardware implementation seems to be the best compromise in terms of satisfying all the parameters. So, and all the references are here, and there were quite a few papers and manuals that I used, but the most part of this thesis was spent in making different tools work and making even different tools to be set up and then test them and debug them. And since I was usually the first user of the tools, all the bugs had to be reported, and that all took a long time finishing. So I would like to thank you.
So any other questions from
if
the
you have any
committee?
questions.